For over 100 years, one theory has pretty much ruled our entire understanding of gravity: Einstein's general relativity. But what if it's not the whole story? Today, we are diving deep into a cosmic detective case using the absolute darkest objects in the universe to hunt for cracks in the very foundation of physics itself.
All right, so our investigation kicks off with this incredible piece of evidence. This is the first ever image of Sagittarius A star, the supermassive black hole smack dab in the center of our own galaxy, captured by the Event Horizon Telescope. But here's the thing. What we're looking at isn't the black hole. It's the absence of something.
And the scientists who actually took this picture, they put it perfectly: a central brightness depression. This shadow, this incredible silhouette against all that glowing gas swirling behind it, that is our crime scene. And hidden right there in its shape and its size are the clues we need to put the laws of gravity to the ultimate test.
And that is the multi-million-dollar question, right? Science isn't just about seeing amazing things. It's about measuring them and then comparing those measurements to what our theories predict. If this shadow lines up perfectly, great. But if it deviates even just a tiny, tiny bit, well, that could point to entirely new physics.
Okay, first things first, let's meet our prime suspect, or maybe the reigning champion, Albert Einstein's theory of general relativity. For over a century, it's passed every single test we've thrown at it. So what kind of shadow does it predict a black hole should cast? So the shadow we're actually seeing, it isn't the event horizon itself. It's actually bigger. So why is that? Well, it's because of a region called the photon sphere. Here, gravity is so ridiculously intense that photons, actual particles of light, are forced to orbit the black hole. Any light that just grazes this sphere is either going to get captured or bent dramatically. This whole effect acts like a cosmic magnifying glass, creating that larger silhouette we call the shadow. And this is where it gets really interesting. This is the key. General relativity gives us this incredibly precise fingerprint. For a rotating black hole like this one, there's a specific solution called the Kerr metric, and it predicts exactly how large and how round that shadow should be, based on just two things: the black hole's mass and how fast it's spinning.
But, general relativity has this nagging problem. It describes the world of the very big: planets, stars, galaxies. Meanwhile, quantum mechanics describes the world of the very, very small. And, well, they just don't play nicely together. So to try and fix this, some physicists have come up with modified theories of gravity. So let's bring in our alternative suspect. So here we go. Let's put our two suspects side by side. On the left, you've got the standard black hole from general relativity. On the right, our challenger, a model called the rotating quantum-corrected black hole. Now, this theory suggests that spacetime isn't perfectly smooth at these extreme scales. It introduces a brand new variable, a quantum correction parameter, that we're just going to call alpha.
Probably the easiest way to think about this alpha parameter is like a quantum dial. If you turn that dial all the way down to 0, you get Einstein's theory perfectly. But if nature has that dial turned up even just a little bit, it would mean space-time near a black hole is different than we thought. And the shadow, well, the shadow would look different too. Our job is to measure that shadow and see where the dial is set.
Okay, so enough with the theory. Let's get to the hard evidence. What did the Event Horizon Telescope actually measure when it stared into the heart of our galaxy? The detectives on the EHT team were looking for two very specific clues in all that data.
First up, they measured the angular diameter, which is basically just a fancy way of saying how big it looks in the sky. Second, they measured its shape. Now, technically, it's called the Schwarzschild deviation, but it's a bit of a mouthful, so you can just think of it as a roundness score. A score of 0 means it's a perfect circle. Any other number means it's a little bit squashed or distorted. And here it is, the first number from the lab. The measured size of the shadow is 48.7 plus or minus 7 microarcseconds. Now, a microarcsecond is an impossibly small angle to measure. It's like trying to measure the size of a donut sitting on the surface of the moon. It's just incredible.
Now for clue number 2, the shape. The deviation from a perfect circle was measured to be negative 0.08, but look at that margin of error. It easily includes 0. So what's the big takeaway here? As far as we can possibly tell, the shadow of Sagittarius A star is incredibly, incredibly round.
Okay,
Now for the real detective work. Scientists take these two measurements, the size and the roundness, and they check them against their suspects. They create these charts that show every possible combination of black hole spin and our quantum dial alpha, and then they just see which of those combinations actually match the evidence.
All right. The evidence has been collected, the models have all been run, and the results are in. It's time to deliver the verdict on gravity. So here's the lineup. General relativity, where that quantum dial alpha is set to 0, it's perfectly consistent with the data. But so is the quantum-corrected model. Because our measurements have that little plus or minus margin of error, we can't completely rule out a small, non-zero value for alpha. It's still in the running. So what's the bottom line? Einstein's theory holds up. It survives another incredibly tough test, and it's still the best description of gravity we've got. But the case isn't closed. The quantum challenger, well, it hasn't been convicted, but it hasn't been exonerated either. We just need a more precise clue.
This brings us to a really fascinating final question, right? The edge of that main shadow is just, well, it's inherently a bit blurry, a bit fuzzy. So if that's not sharp enough to give us a final verdict, what clue out there could possibly be more precise?
The answer is the photon ring. This is a razor-thin ring of light made from photons that have orbited the black hole multiple times before finally escaping and reaching us. This ring is an even more direct probe of space-time right at the very edge of the black hole, and its shape is a much, much sharper fingerprint than the shadow itself.
We can't quite see it yet, but future space-based telescope missions, like the proposed Black Hole Explorer, are being designed with this exact goal in mind, to capture an image of the photon ring and use it to make the most precise measurements of gravity ever attempted. This cosmic detective story, well, it's really only just beginning.